say it on this other side here. Quantum mechanics, I'm considering here two experiments you might do, sort of idealized experiments. Here we have a laser which is emitting a single quantum particle, a photon, and this single photon goes along, and in this case it hits, well, what you could refer to as a half-silvered mirror. If you're an expert, you call it a beam splitter, but it's the same thing, basically, except it's not silvered at all, usually. But think of it as a half-silvered mirror. Half the light that impinges on it is reflected, and half it is transmitted. Now, you might think that that means half the photons go this way, half the photons go this way, and in fact, you could indeed confirm that by putting a detector here and here, and you would find that either this detector clicks, or this one clicks, whatever it does, to register the photon, and it's either one or the other, not both, not neither. Well, that would be true if it were an ideal experiment. Of course, in practice, you might find you lose the photon sometimes, or what have you, or one of them goes off by mistake, or something like that. But if they were perfect, it would be either this or this. And that's fully consistent with the idea that this is a particle at the screen here, at the beam splitter. It decides either to go this way or this way. That would make sense. However, you can do a different experiment where you supply two new ordinary mirrors and another beam splitter over here, and let's make all these path lengths equal, and let's have detectors here or here. So the two things the photon might do when it reaches here, it might go this way or this way. But there are really four things you could think it could do. It could go this way, that way, this way, this way, this way, that way, and this way, this way. And what you find is that the two routes which end up here, in some mysterious way, cancel each other out, and it always activates this detector. Now, that's completely mysterious, because if down here it decided to go one way or the other, by the time it got here, each possibility could decide to go one way or the other, and so it should equally have the chance of doing one or the other. That's not what happens. It's always one of them. And how do you understand that? Well, the way it's understood, I should say this is a sort of particle-like behavior of a photon. This is a wave-like behavior of the photon. And it would make sense if you think of these as being little waves, and then the waves would either reinforce or cancel each other out, and that would explain this. But then it doesn't explain that one. So you need them both in some sense. And the way one understands that in quantum mechanics, if I can use the word understand in this context, is that the two things which it might do, either this route or that route, in order to get here, have to be somehow superposed. So it does both at once. That's a strange thing to say. It does both at once, and it's weighted by these funny numbers here. Now, you might think those were probabilities. It might have a certain probability of doing one and a certain probability of doing the other. But then you'd never get cancellation. Probabilities don't subtract, so they just add up. So what these numbers are, they're complex numbers. These are the numbers in the vessel plane. Here's our vessel plane again. And you have two procedures that you have to consider. One is what's called unitary evolution, and that's what the U is doing. And it's basically the Schrödinger's equation. And Schrödinger's equation tells you what happens if you don't make a measurement. So I'm not quite sure if making a measurement is looking at the detector or listening to it or what, or whether the detector itself has made the measurement. That's an intriguing question. But whatever it is and whenever it is, at that point you do something else. So if you, before the measurement is made, you do this U thing, which is what's called linear, and I'm going to explain what that means. Well, let me explain what it means now. So that's, rather than leaving you in suspense, what does it mean? Well, here we have here we have an experiment, a laser again, and the photon or particle, whatever kind of thing it is, let's say a photon, comes and hits this green thing and produces a lot of junk. Or there might be a mirror in the way, and it hits the brown thing instead and produces a lot of different junk. But if this is a beam splitter, then it goes through both at once in some strange sense. And so linear says that whatever happens this way, and all the resulting consequences of that action, have to be added to, or what's that mean? Well, superposed in some sense, to all the things that it must do if it goes the other way. So that the quantum mechanical state of a system is both at once. It's a superposition of those two alternatives. And that's what you have to consider. But then when you make the measurement, suddenly you do something quite different. You somehow consider the numbers. You see, these are two, the Z and the W in these weighting factors here. They're called complex amplitudes. You plot them in the vessel plane. You see how far from the origin they are. Square, though, that's what these mod bar things. You take the square of the distance from the origin, and then the ratio of the two probabilities of one happening or the other are given by this. This thing called the Born rule. And if you combine these two things, you get quantum mechanics. The trouble is that there's this thing called the measurement paradox, or usually people call it the measurement problem, thinking that it's going to have a solution within this scheme. I just think that's not going to happen. It's a paradox. It really is an incompatibility, because you could say, why don't you treat these detectors as though they were part of the quantum system? After all, if quantum mechanics is a universal scheme, it ought to include the behavior of the detectors as well, and so therefore you have a superposition of this one registering and this one registering, not this one registering or that one registering. Well, that's what happens, one or the other. Well, there are endless different ways that people have of coming to terms with that, and I'm not going to go into all that. That would take the rest of the talk. I'm just going to impose upon you my own view, which is, well, I'll come to that. Let's slightly change the experiment. And here I've got a laser again, but I'm going to do something rather nasty to a poor cat. Not my idea, it was Schrodinger's idea, I should say. I should also say it's a thought experiment. He wouldn't have considered doing it. He was a very humane person, and I don't think he would have considered actually doing an experiment like this. And in my discussion in the Danish lecture, this was the mermaid, and the mermaid, you see, there's a part of the story when a photon, well, when the sun comes up, you see, and as soon as the sun comes up, the ray of light strikes her and she dies. So what you do is, well, that's the mermaid, you see, and she gets killed. So you reprove the mermaid by not doing that particular nasty experiment, but you do this one, you see. You put a mirror there in the way, and the cat or the mermaid is reprieved, is alive, you see. Of course, the story doesn't end there, as you know, and that is that you put a beam splitter in there, and what happens to the poor cat or the poor mermaid? Well, superposition of life and death. So it's a kind of limbo situation. Schrödinger was really saying this, of course, is ludicrous, it's nonsense. My equation, he would say, that's Schrödinger, not me, of course. Schrödinger would say, my equation tells you that this is what happens. And that's absurd. There must be something wrong with my equation. He didn't quite put it like that, but I think that's what he meant.